These are things called Clifford parallels projected down into 3 space. They're the lines, and they kind of fill the sphere. I really don't know. This is Roger Penrose's lecture on twistor theory at Cambridge, which he gave a few weeks ago.
And here we in fact have the sort of twistor picture. On the left-hand side we see a space-time picture. We imagine that's 4 dimensions. And a point is represented in terms of all the light rays passing through it. And the light ray is represented as a point. So if you think of light ray space, then you have the 5-dimensional space. Now, it's not really the boundary of anything as it stands, it's just a nice way of looking at things. But why did I think of this as a good idea? Well, the idea really came from, this was when I was in Austin, Texas, and I had a good friend, Ivor Robinson, who was an Englishman, who the Americans loved because he had such a wonderful way with words. He never wrote anything down, it was always in words. So if he wanted to write a paper, he'd have to persuade somebody to become a joint author. But he did have great ideas too, not just words. And one of his ideas was to construct solutions of Maxwell's equations. You can imagine solutions which are based on null rays. People were very keen on null solutions, which null means that the principal directions point to both the invariants vanish, that's the simplest way to say it. And you have one null direction in which the Maxwell field points in a sense. And you have the congruence of these directions, and you have a shear-free congruence. And one of these easiest to describe congruences is you take a light ray and you think of all the other light rays which meet it, and that gives you a shear-free congruence. And so you could construct solutions of Maxwell's equations based on that light ray. But Ivor's idea was, why don't you displace that light ray into the complex, and the light rays which are trying to find it, they can still be real. So you have the light rays which are in a sense meeting that complex ray. And you still get a congruence of real light rays. They're still shear-free, but they rotate. And they can twist one way, left-handed or right-handed. And it seemed to me it was a nice idea to think of the light rays instead. But I had no idea initially what is the family of rays which meet null ray. I had thought about that for a bit, and I did realize that you could describe that family of rays in terms of Clifford parallels. I think I need to come to my next picture before I go into that. Let me do it. You see, this is we've got that on, a version of this picture on the heading of your paper, whatever it is. This is a picture of Clifford parallels. So you imagine a 3-dimensional sphere, and the Clifford parallels, which I did know about, it's a family of great circles on the 3-dimensional sphere. It's a 2-dimensional family of great circles. They fill the whole sphere. They always miss each other. There are no intersections. They all link each other, and they make this wonderful twisting picture of linking rings. So you have to imagine that this picture if you take a 3-sphere and you project it stereographically into 3 space, then the Clifford parallels in the 3-sphere project down to a configuration like this. So that was what there was, and we see the ring in the middle, and then there the straight line, the outside with the arrow on it, is also a circle. It's one which goes through the points to infinity. You're projecting stereographically from, and so it becomes a straight line.
So that I don't know enough. I don't know enough weird geometry. Toby knows all about these things. Maybe that's... I don't know what that's about. But I do like the picture. And it reminds me of that thing about magnets that I just did. And I was going to be a bit more organized about this. I jumped ahead in my book on Henri Poincaré. I skipped a lot of really gnarly maths. And I came to this idea of the skeleton of a torus. Did you know that toruses have skeletons? Look. That's the skeleton. And it's because when you cut the torus in horizontal planes, like this all the way up, you either get a plane with one blob on it, which is that cross section, and that's a one blob. That's reduced to a line in the skeleton, because there's just one blob when you cut here. But when you cut here, you get 2 blobs, and so that's doubles. I'm going to join up again at this point, because after that, when you're cutting, you're only getting 1 blob. So it's as if one blob has split into 2, and then gone back to 1, and then gone to nothing outside. So that's the skeleton of a torus. And this was an idea of Henri Poincaré. And then he can draw the skeleton of a torus with a bulb attached. So you can see that at some places there are actually 3, and at some there are 2. So here there are 2, but here there are 3, and here there are only 2. I don't know why he did that. I haven't read this, I just saw the pictures. He hangs these pieces together to kind of reconstruct them. And then he's doing algebraic geometry on this stuff. Solutions to equations. No, he does the identifies points to make a cylinder. And a Mobius strip. And there's this fun bit. This is what I stopped at. This is a torus, but this thing has been twisted. Before you join these, you twist them around you twist one of them through 360 degrees. And so a path on the torus has to flip by the time it gets around. And just bring my tea. So I don't think very well sitting there. I don't think. So I was thinking about this thing. As you flip, if you imagine this turning into that, you would be switching these two over here. Oh, there's so many ways to interpret this thing. I've no idea what I'm talking about. No idea at all. But if you've got paths running around long ways around this torus, and the paths have got a twist in them, they're going to match up when they get here, but the twist is going to be a mirror image. No. It's always going to have the same chirality, isn't it? It's going to be if it has a direction on the line, but Poincaré's diagram doesn't have a direction. These things aren't oriented. This isn't a left or a right-handed twist because there's no direction on this path. You don't know whether it's doing that or that. Poincaré was interested in homotopy and homology. Each cycle, what's a cycle? A cycle is a path around the every cycle in the three-dimensional manifold is homotopic to a cycle in W. So all questions about the homology and homotopy of V can be transferred to W. What are V and W? The surface W is visible on the handle body as that part of the sphere that lies outside all the disks, together with the boundaries of the disks. As a surface on its own right, it can be supposed to be obtained from an octagon by identifying sides in pairs. Two cycles. Look how complicated it got. That's just hilarious. What's octagonal about that? 1, 2, 3, 4, 5, 6, 7. My goodness. Why is that an octagon? Because the 7, oh yeah, because this is, it's because, no, there should be 8. If there are 8 vertices, then there are 8 edges, aren't there, to an octagon? So why are there only 7? Let's try and see what shows you where those come from. Computing the Euler number of a torus. It's hexagons. It's about his is this the octagon? And that is topologically an octagon. Whose edges are conjugate in pairs, two conjugate edges corresponding to two sides of the same cut. There's nothing quite like reading way out of your depth. I often do this. And then I think, well, one day I really ought to study this and actually learn something. He ends up producing a group of direct symmetries of the dodecahedron. Anyway, let's leave Poincaré for a while. That was interesting, wasn't it? And I was just after watching Janet's video, hello Janet, about the how do you find the center of a triangle. Your argument was, I thought you'd pretty much done it, because remember we had this thing. I was thinking about the converse, how it's not necessarily true that that's the center of the triangle. But then I found that that magic thing, that whatever crazy quadrilateral you draw, if you join the midpoints, you always get a rhombus. Isn't that amazing? So it means that any old way that you project a quadrilateral, you can produce a kind of rhombic tiling of it. If you identify these edges in a repeating pattern, how am I going to do this without messing it up? That goes out to about there. That goes out to about there. Sorry, I wasn't pointing in the right place. So you then have one of these in here. Something like that. I've messed it up. Now, why have I got a pentagon here? Oh, because that's supposed to carry on. So that's one. Oh, this thing is supposed to carry on where? Up to there. And you could carry on down this way and up that way. I've definitely lost the plot, haven't I? We were talking about this being some kind of stereographic projection onto the two plane of an equilateral triangle lying at some angle. Like that one is the equilateral triangle flat on, but here this could be equilateral if that was kind of at that angle. No, except it wouldn't be, because that was absolute nonsense. That was nonsense. This whole thing is rubbish. I'm just talking absolute nonsense. But it's fun playing with ideas. But your argument, I know what I wanted to actually talk about, is your argument was if you have an equilateral triangle, let's see if I can draw one. That's equilateral-ish. You have, it's equilateral, so if you cut that edge in the middle, you have a line of symmetry. And if you cut that edge in the middle, you have another line of symmetry. And if you cut that edge in the middle, you get another line of symmetry. And these lines of symmetry you can think of as reflection, axes of reflection. So if you reflect that in that axis, it stays the same. And if you reflect that in that axis, it stays the same. This line moves to here and this line moves to here. But points on the axis under reflection don't move. So what you have is a point where these three meet, which doesn't move under any reflection. Now, the same argument holds if these are kind of rotations. So if you rotate that axis to there, that to there, and that to there, you're rotating this whole triangle through some sort of circle, slowly through a circle. And stopping every 120 degrees. Well, my argument then is that I think you can do this with algebra if you if you call the reflections R, S, and T, and you call the rotation R. No, we've already used R for reflection. What do you usually use in groups? It's so long since I did groups. What do you usually use for rotations? Let's just call them A, B, and C. So if A is 120, V is 240. And C is 360. You can achieve any of those by composing two reflections. Because the angle between these reflections is 60 degrees. If you reflect in that and then reflect in that, if you reflected in that, you would get to there, and if you reflected in that, you'd get to there. So you would be doing an A. If you did a T followed by an R, you would get an A. So you can fill out this group table. This is your identity reflection, which does nothing. This is the action of composition. So we have a group here which is C, A, B, R, S, and T. And if you fill out that table, you get a group. But why was I trying to connect this to? I wanted to sort of say that because the reflections leave all the points on the axis unchanged, any two consecutive reflections will leave the points on both axes unchanged. But if a point on this axis will be moved by this reflection, and a point on this axis will be moved by this reflection. So the only points that aren't moved, the only point that isn't moved is the center. So that's a very convoluted argument about why this is the invariant point under this group acting on this triangle. The rotation must then be about the center, but then you get this thing with the center of a circle. It is the rotation, the general rotation in a circle is going to leave all points here stay on the circle, and all points in the center stay on the center, and all points in between go to that's the mandala thing that I was talking about. Why was I talking about that? In the comments, this Jungian archetype that also appears in Buddhist scriptures, and it's a circle, and it figures a lot in Aristotle. Aristotle talks a lot about circles and their mysterious properties. But the only single point that this rotational group, this is a continuous group. You can represent it by a 2 by 2 matrix. Well, I can't remember what goes where. You've got cosines and sines of the angle in here. And this matrix acting on a point anywhere in the plane. So say it's something like cos sine minus sine cos or something. I can't remember what it is. And x and y, if you multiply that through, you get how does it work? You have an axis and a point 0, 1 and a point 1, 0. And it rotates it into through theta to that goes to there and that goes to there. So 1, 0 goes to cos theta sine theta, and that point goes to, I think it's something like that, minus sine theta cos theta. I can't remember how to do these things. These are the images of 1, 0 and 0, 1. That should give you the formulae. Whatever you, when you get this right, that gives you the formulae for the x, y in the new coordinate. Well, this is a rotation of the points. There's another issue about whether you talk about rotating the coordinate system, in which case that is a negative rotation, because this point, this is rotating the point through theta, but if this is rotating the axis through theta, then this is the equivalent of a minus theta rotation of the point in the new coordinate system. And you have to get these things clear, and that's a big part of undergraduate mathematics. Is just making sure you don't suddenly start talking about positive numbers when you should be talking about negative numbers, and vice versa. And that's why doing geometry at the level that Poincaré did it is really hard. You've just got to be very, very careful. But actually that homotopy stuff didn't seem that hard, right? So I'm sorry, Janet, I know too much maths and I'm wrecking it for you. I'm making it all seem horribly complicated. So I better not upload this video because it's crap anyway, isn't it? But I did enjoy that. Maybe one day I'll upload this, maybe I won't. Bye.